Welcome in this third video on data processing with EEGpal. Now we are going to see the interpolation, which is the standard way to deal with bad electrodes. See on these pictures with the bad electrodes in the center with the signal contaminated with a lot of high frequency noise. The interpolation will remove the signal of this channel and reconstruct it based on the signal of neighbor's channel. In this way, the layout is preserved because the number of electrodes remain the same. Okay, let's open the interpolation model. In the right part, you have a table of checkbox with in column H channel and in line H file name. You can choose which electrode you would like to interpolate. The third column gives you the percentage of electrons you have chosen for interpolation. As a general rule, it's better to not go higher than 10 or 15%. In the left upper part of the windows is the automatic fill tools. The first tool is the bridge detection in order to fill the table with the bridged channel. It depends on if you have run the model bridge detection in a previous step in the same session, or if you load processing parameter file which contain the detection, or you have the possibility to load the Excel sheet which has been generated by the bridge detection module. The second tool is the flag bad channel from the clean raw data plugin of EEGlab. This option is available only if you have activated during the processing with the filtering plus model. If you have done that, you can automatically fill the table with its suggestion. However, I strongly recommend to perform a visual inspection of its suggestion because they are not always good and sometimes too conservative. For your inspection, you have the possibility to directly modify the table, or you can work in an external file. You can export this table with this button with the Save Table As, and you can save it either in Excel or CSV. This table is similar as the one you have seen in bridge detection. You can put a 1 when you want to interpolate a channel and 0 when not. After your inspection done, save the file and you can load it into the interpolation model. And it will automatically fill the table as you did. The difficult part of this step is how to choose the electrode to interpolate. First of all, I will interpolate all the electrodes that I have ignored for the ICA decomposition. Then, to do the inspection, I write a manual inside of the FAQ section of the module manual, which proposes you a procedure to inspect your data with event-related potential study or with continuous data. Before to process, you have the choice between two interpolation algorithms. The first one is the 3D spline based on a paper of Perrin in 1989 using a script developed by Mike X. Cohen. This is the strategy used by the Cartool software. Alternatively, you can use the Spherical algorithm, which uses the function popInter developed by Arnaud Delorme for EEGlab. Finally, as usual, you can define the option of output with the output format, the folder where to save the data, and the suffix string for the file name. Then press on Run to proceed. Now we are going to talk about the re-reference model. In EEG, as you know, you measure a difference of potential between one electrode of reference and all the other electrodes. The EEG signal strongly depends on the choice of the reference electrodes. For example, here, if I choose to reference everything to the OZ, you see that the signal completely change. It makes the comparison between scientific paper difficult. The most popular is to use the average reference. It means that you create an artificial reference electrode by averaging all the electrodes. And you perform that easily in EEGpal with the re-reference model. So this one is very simple. You choose which channel you want as reference, so by default will be the average, or you can choose the one that you want, and then you just define the output option as usual. And run. The last processing step is to cut the signal in several time bins that we called epochs. To do that, we use the epoching model. The right part of the epoching model windows is composed of two tables. The first one is to define the epochs, and the second one permits to define some rejection criterion to remove some of them. For the epochs definition, we will see two cases. The first one is file which contain marker or trigger to define events in the recording, which is usually the case in an event-related potential study or called ERP. The second case is with continuous recording without any events, like for a resting state. Let's see the first case. So you can specify if you want that EEGpal detect the events in file, which is the case for BDF or set format, or if it detects it into the MRK file, which are generated with all the other file format, like the SCF. Here, EEGpal will list all the events that it has detected. If you know that there is a systematic delay due to experimental screen, for example, you can correct the position of the events here. In this dataset, I know there is a 26 millisecond delay. I can specify either in millisecond or in time frame. You can notice that when I enter 26, it changed to 25.4 because it adapted according to the sampling rate of the data. Here you can define the event of interest that you want to epoch. In this case, we are interested by the event 1 for the face presentation and 2 for control stimulation, which are cars. Then you need to define the onset and offset of the epoch relative to the event. In our case, we are interested by 100 milliseconds before the stimulus presentation. It's why I put a negative value. So it means that my epoch starts 100 milliseconds before the stimulus presentation. And then the offset, I put 300. So mean my epoch will end 300 milliseconds after my stimulation. So it means that I have a total duration around 400 milliseconds. Again, the value are automatically adapt to the sampling rate. Now let's see the second case where you have a continuous recording without event. So in event you will have nothing, and for the epoch you are going to specify all the file. You press on this button EOF, which corresponds to end of file. It will consider all the file length. Then you can cut into sub-epoch with a specific duration. For example, you can cut your file in sub-epoch of 2000 milliseconds. And you see that EEGpal compute that they will have 341 sub-epoch of 200 milliseconds. For the next part of this tutorial, I will come back to the first case of an ERP study. Now let's talk about the baseline correction. The idea is to correct the baseline inside of an epoch relative to its mean value. It means that you are going to subtract the mean value to every time point. The purpose is to correct the baseline shift inherent to electrophysiological recording, which was not already corrected by the high-pass filtering. It permits to make the epochs more comparable between them, and it has also a beneficial effect on the artifact rejection. There is two main accepted solutions. The historical way is to define the signal before the stimulation as baseline. However, it's assumed that there is no brain activity linked to the task as anticipation, which is rarely the case. It's why the more popular way is to define the baseline over the whole epoch. If you want, you can even define your own period of baseline. You see in this interface that we have different options between scalp channel and auxiliary channel. It's because EEGpal allow you to process differently the auxiliary channel than the scalp channel if you have defined those type of channel into the electrode setting option. Here, you're going to define the saving option for your epochs. The default option is to save all accepted epochs merged into a new file. It is useful for frequency analysis. You have also the option to save one file for each epoch. Now let's see the artifact rejection. The purpose is to remove all bad epochs contaminated by remaining artifacts like eye blink, movement, or cough. An amplitude bump into a short time period is the sign of those artifacts. EEGpal proposes you three different thresholds for automatic rejection of bad epoch. The first is the maximum absolute amplitude. If the signal inside of an epoch reach the specified threshold, the epoch will be rejected. The standard choice of our lab is between 80 to 100 microvolts, because the signal of the brain has very low probability to reach this amplitude. A signal which reach this amplitude is more likely to have a muscular origin. This is the same criterion as used in the CarTool software and can be found in many publications. The second is the max step threshold. It defines a maximum size of the signal bump. In this case, the epoch will be rejected if it contains a bump higher than 30 microvolts between two time points. The third is to define a maximal range of amplitude between the smallest and the biggest amplitude value in the epoch. It is quite similar as the max absolute threshold. As for the baseline, you can specify a different rejection criterion for the auxiliary channels. For example, if you have kept the electroencephalograph as auxiliary channel in your data, you can use it to reject brain epochs based on it. There is no universal threshold in the scientific community. You will probably need to make some tests and adapt it. The important is to report those values in your article. If you want to explore different thresholds, you can help you with the AR evaluation tool, which permit to generate two summary Excel sheets about the rejection. Before to run it will require that you define the output folder. Here is the two output file. AR testing summary will summarize how many epochs was rejected or keep. So I'm interested to the last column, which is the percentage of total accepted electrodes. Then the second file summarizes the percentage of epochs rejected for each of the electrodes. It permits to see if one electrode is responsible for the majority of the rejection. If it's the case, it could be a good idea to interpolate it. Finally, let's define the parameter to generate the ERP. In this section, you can average all the accepted epoch to generate ERP file. With the per trigger option, you can generate an ERP for each of the event you define, and all trigger will merge all the events that you defined. You have two columns. The first column, the within subject, permit to generate an ERP file for each of your participants, which is what you want to perform a statistic. With the between subject column, you can generate an ERP by averaging all the participants together to generate one single grand average. In both cases, it is important that you have specified which subject correspond to which file with the method we have seen during the first tutorial video. Then specify the output option as the output file format, the destination folder, and the suffix string in the file name. For the within subject ERP, you have the option to generate one folder for each participant or to put all the file in a single folder. In the output destination folder, you see that he creates one Excel sheet epoch summary, which is basically the same as the ER testing summary with inform you about how much epoch has been accepted. Then you have one folder which contains the between average, so the grand average with all the participants together. Average within, so where we got one average for each event and each participant. And in epoch subfolder, you got the file with all the concatenate epoch. This concludes this series of tutorial video on the processing of EEG data with EEGpal. In the next video, we will see how to batch in order to automatically execute all those steps in a row.